Let's briefly, I'm going to try to run through this section really fast because one of the things you're going to see is a whole bunch of configuration details in here that we won't have time to get into, but they're in the handout and they'll be there for reference and so forth. So I'm going to try to hit kind of the high points in this security work. Also, there is an area we didn't really talk about, layer 4. Layer 4 is basically how that communications is handled between host devices. There's basically two ways to do it. One is referred to as TCP, or Transmission Control Protocol. It is the, quote, guaranteed protocol because there's this two-way handshaking that occurs between that host in the device. I've always used the analogy as like mailing a registered letter. You drop the letter in the mailbox, the receiver gets it, you're going to get what? A receipt back. And that's kind of how TCP works. It works again by this handshake that occurs to first establish a connection, and then information is sent, it's acknowledged, more information is sent, it's acknowledged. If an acknowledgement does not occur in the certain time frame, then that information is resent again. And a ladder diagram is commonly used to illustrate that process of send and get an acknowledgement. UDP, or User Datagram Protocol, is referred to as a connectionless protocol. That's the best effort. There is no feedback. In other words, information is just sent. It's like mailing a letter. You drop it in the mailbox and you hope it makes to where it's supposed to. Typically, this is used where latency is more important than the data loss. Remember, again, because of the OSI model, we're at layer 4. If there's data loss, that's another layer's problem to deal with that. In other words, above layer 4. And again, we also have a similar ladder diagram. But one thing to keep in mind, that TCP, three-way handshake, is used to establish a UDP session. Once the session is established, though, the data is just sent.
So it has to answer
one time. And after that, of course, again, if something disrupts or corrupts the data, it's just gone. And again, it's up to a higher layer to deal with that. A lot of times that's dealt with at the application layer. And think about artifacts you see in streaming media applications. You see what you might hear some blips in the audio, that's just gone. A lot of times, a lot of the streaming media, and certainly the voice over IP applications, they use the last good bit of data. They just replace it. And if it's short enough, you don't even know it. Okay? In video, you often will see what? Some freezing, some strange looking artifacts. You might see a freeze frame of the last good video. Well, that's that application deciding, how do I deal with the missing data? Okay, different applications will do different things. A Streambox video codec will output its internal color bars if it's got too much loss. So all of a sudden you see these color bars up that say Streambox on it. You know where they came from. I've either lost my interconnection or I have a really, really bad data problem. But that's the application layer that's making that decision.
The Harris and the other digital STLs that do HD or whatever, they use UDP, right? And they're right.
I don't know. They could or they could. Now, wait, let me back up. Well, let me back up a second. They can, normally, again, UDP is used for time-sensitive media. But you can use TCP, and what you find is increased delay. And how they get around that, they have buffers in the receive unit, okay? If the delay is not an issue. TCP can be used for streaming.
Well, in the encoders or whatever for HD, you have to set it for TCP/IP or UDP.
Okay, they let you choose which one.
Well, and UDP, TCP is if you got direct internet connection
Right.
to the exciter,
Mm-hmm.
and then UDP is if you're using a digital STL.
DL, okay.
So how did they ever get that first act back?
Well, remember that Harris Digital STL is not an IETF compliant host device. You can do a lot of things in a proprietary environment. The context of all of this is in IETF compliant devices, okay? Again, a comparison chart between the two and so forth. TCP is a little bit more complicated because of the header. The UDP is a lot simpler. It's also a lot faster because it is simpler. Also, there's real-time protocol, and this comes into play often in broadcasts, and particularly streaming media deliver. It's a way to basically, it is implemented within UDP. So the transport is UDP, but the real-time protocol is basically implemented, and it basically does two things. It time steps the data for putting it back together in some way similar to the precision time protocol that is time stamping packets. This is time stamping UDP packets so they can be reassembled in the right order. And also it has a feedback mechanism so the receiver can send back performance information to the sending host, which could be maybe slow down, maybe you can speed up, whatever type information that goes back and forth. And again, it is information that is basically generated at layer 5, okay, and is encapsulated in the payload section, and it has an associated RTP header that, again, it's encapsulated within UDP. Port numbers, we talked about this a little bit. Port number is simply the way that hosts differentiate multiple applications that exist on them. Port numbers can be registered. There is basically port numbers range from 0 to 65,535. Within that range, there are 3 different classes of those. An important thing to keep in mind, UDP ports and TCP ports are independent or different. They're independent. Although some protocols use both UDP and TCP, a couple of them. DNS is one popular one that does that. Again, there's a URL for all of the list. This is a little reference, another one of my Packet Life Net reference charts, or what are considered in their view of common port numbers that you'll find. Again, DNS is 53. It will use both UDP and TCP. Most of these, however, are going to be TCP port numbers. This is my little short list of common ones that hopefully most of those are you're familiar with, or at least some familiar terminology. So when we take we create a socket by taking an IP address and we put a port number with it, we've created a socket. Okay, so a socket is a combination of a IP address and a port number, and the port number is separated now with a colon. And of course, this again is the way that applications are indexed. Again, multiple applications executing on a host device. So how does the data get to the right application? That is done by the port number. So let's quickly build a network. We have generally three types of devices we can work with. We have a layer 1 device, which is a hub. We have, of course, layer 2 devices, which are switches we've talked a lot about, and we have our layer 3 devices. We want to eliminate hubs from our environment, okay, simply from a performance standpoint. It is a perfect way to degrade network performance. And from a cost standpoint, actually, it's probably impossible to buy a hub today, unless you're looking for legacy equipment on eBay or something.
But it's good for your toolkit.
Maybe. It depends.
It depends.
It depends. Why do you say it's good for your toolkit?
Well, because it gives you a sniffer opportunity in a circuit going by.
But I'm a good network administrator, and I'm anal about security. So well, what it's going to do, I'm going to implement switch port security, and I'm going to limit MAC addresses on my ports. You come along and plug your hub in, all of a sudden I'm going to have more than one MAC address. And what am I going to do? I'm going to shut that port down for people just like you that's sniffing my network. So again, it depends. It could be useful. Right, but a hub is like a multi-port. Yes. Oh, yeah. Right. That's right, but he's going to plug it in between that port and the host that you're interested in. Hubs used to be a lot more useful than they are today.
So now what you're using is the mirroring in a
You're
switch.
using the mirror, or you use a physical tap. That's the other way to do it. Physical tap.
But hubs are still real useful. I mean, for door stops and props.
Yeah, there you go.
What's a physical tap then, would you?
Well, they have Google network taps. And you'll find, there's a tap for, a twisted pair. There's for certainly if you're doing fiber, there's optical taps. And it's basically a 3-port device. In my troubleshooting deal, I have a whole bunch, show a bunch of those deals. I can send you a couple of ones. Even go to eBay and, Google taps. You'll find all kinds of stuff. Just go Ethernet taps and you'll come up with all kinds of stuff. Networks typically in the early days, back to the bus structure, were considered a flat network. In other words, everything was equal on the network. Everything was in a single broadcast domain, but that had a lot of problems with it, particularly in scalability and performance. So today we want to build segmented or hierarchical networks where we're going to now separate host devices either. Well, there's a lot of reasons you can separate. Generally, you do it for security and performance to separate devices. Several of the reasons, again, you might do it based on some kind of regulation. Maybe a corporate network probably has some policy that defines how you're going to segment networks. If you're in the financial industry, there's federal regulations that define how you build financial networks and from the architecture standpoint, particularly if credit cards are involved. So in our network, again, this was back to our network we built earlier. Some of the things to take into consideration in design is the addressing, of course, security, and picking out hardware, and that's where I wanted to get to. Again, I'm going to skip through this stuff, just kind of some kind of textbook architectural concepts, kind of the classic approach of you'll hear terminology talking about the core or the backbone or distribution level, down to access, which access is those, say, switches that the host devices are going to connect to. Several things to take in consideration when you're buying Ethernet switches. One is the form factor, and certainly we can have self-contained switches. We can have stackable switches, which on the surface look like standalone switches, but really there is some method to loop the back planes. Typically on the back they have what's called a looping cable that allows you to loop the back planes together rather than using access ports to connect them. Again, all kinds of things to separate in terms of the physical, the port density. Important to look at this processor, memory, how many addresses or how many MAC addresses are supported, multicast capability, again, a lot of options, PoE requirements. One thing to caution with PoE, just because I have a 48 port switch does not mean that I can supply 25 watts of power out of all 48 ports of that switch. More than likely, that switch is going to have a maximum amount of power it can deliver, and you may not be able to enable that on all ports of that switch. Some switches, in my example, I don't know if you've noticed, but on some of the Netgear one, they had a group of ports that had a yellow box around it, and those were the PoE ports. The non-PoE ports were the other ones, and so forth. Kind of the same thing on routers. You can buy routers in standalone or modular, in fact. Again, a lot of different feature sets, and primarily with the router, the interfaces is really going to drive that router. In turn, that drives typically kind of processor capacity and so forth that is determined. Again, I'm not going to spend time on some of the what I think of as some of the details in the weeds in the interest of time. Again, all of these slides you'll have access to. Of course, when you do private addressing, most likely you're going to need some public interoperability, so you're going to use network address translation for that. This is where we get into actually building some stuff, and I am going to go through this real quick.
What's the difference between NAT and port forwarding? Are they the same thing?
Well, port forwarding is a function of NAT. Okay, it's not the same thing, but it is a capability of a function of NAT. Where I have on my public side are to use the proper terms associated with an outside network and an inside network. On the outside network, I have obviously a given port that I'm receiving a public IP with a port number. I'm going to translate that through the IP address to a inside IP address, okay? Am I going to maintain the port number, or am I going to make it something else? And that's where port forwarding, and it can be two ways. It can be I'm going to maintain the port number, but I might translate that port number to something else, okay? This is simply talking, this gets into configuration and stuff. Again, this is the stuff I'm going to skip through, and if you have some interest here, how about we just talk about this after after class. Basically what this is saying, generally equipment out of the box, you're going to start out with a command line type interface, okay, to get enough information in the switch to get it going. Then you might choose to use the graphical interface that most manufacturers have. If you do a lot of configuration, you probably like the command line better. Most people can run that faster than they can go through a bunch of check boxes, but that's a personal thing. So some details. We talked about building VLANs. Well, how do you really do it? Well, from a conceptual stand, this is kind of the steps you have to go through. And this is the detail of actually commands that you would enter in the Cisco environment to build the VLANs between those two switches. Basically, you're going to, this would be the actual configuration deals. This is an example of within Cisco, they do have some error checking. If you type some wrong, it will tell you not necessarily what you typed wrong. It'll just say you typed something wrong in that command. Okay. Same thing, a little bit different, but for the other switch. And now we've built the VLANs. How about in the Cisco to HP environment? Very similar deal, but remember the terminology is a difference between the two. So what is access in Cisco is untagged in the HP world. Another little chart with some really funny background colors that just compares the terminology between those two nomenclature sets. Routing, in terms of implementing RIP, that's pretty easy to do. In a small network like we just built with our VLANs, RIP is certainly adequate for that. This gets into kind of some hands-on part of the longer version of this, where we actually have some equipment and built. If any of you happen to have been at NAB for the NS workshop about 3 years ago and showed up at 8 o'clock on a Saturday morning, we spent the morning actually doing some of this with the real equipment and so forth. And this gets into what I think of all the weeds of actually configuration of how we're going to build a network and address a plan. I did want to spend a couple minutes to talk about IP addressing. And let's think a scenario, a network where we have we've established 3 VLANs and we've counted up how many hosts that we have to put in those VLANs. We want to throw in something for a growth factor. Okay, we don't have to readdress everything. So let's put 20% growth into our design. So what size subnets we have to have? Well, remember our subnet chart that defines how many hosts we have. So if we need 10 hosts, we're going to have to use these block sizes. So we're going to have to use a network that supports 16 hosts, right? Because 8's not enough. And likewise, we need 15. We're going to have to use a subnet that can support 32, and likewise for our network management network, which is a fairly small one, we would have to use a subnet that would support 8 host devices. And again, we build up then, and how are we now going to divide our IP addresses? And let's say we have a base network of a private address or a private network with a /25 that happens to be half of a Class C, which is 128 hosts. How do we address the IP plan? Well, there's several ways to do that. One, simply use your favorite subnet calculator and develop a plan. In other words, you engineer it all on paper, makes it easier to interface. We talked about using a trunk interface and a virtual interface. There's some of the details of actually implementing that with sub interfaces or virtual interfaces on the router side, trunk interfaces or tagged interfaces on the switch side. Again, start to add more detail to our network. And what is wrong with our network? Well, from a performance standpoint, we might have done something not too smart. We have a switch that's capable of gigabit Ethernet, but we're using, let's say, a fast Ethernet or 100 megabit port on that end. Okay, maybe not the best design approach. So what could we do? Well, we could use maybe fiber connectivity between our switch and the router, but oops, the router doesn't have a fiber interface. So maybe what we have to do is now we have to add a different interface board, because that is a modular router in terms of interfaces. And of course, you got to rechange the configuration and do that. And that's some of the stuff that we went through. And another approach is simply, well, use a layer 3 switch in that application. Perfect example to where a layer 3 switch would be a really simplified way to handle in that. Okay, questions? Okay, sorry about running through that, but this is this is where I wanted to get to, and again, keep